think we can start with the talk from Vice Jill. He comes from Virginia Tech. And he's going to tell us about his work titled Achieving Debugging and Interpretability in Federated Learning Systems. So, Varis, I hope I'm pronouncing your name correctly, and the floor is yours.
Hello, everyone, and thank you, Javier. I'm Waris Gill. I am a third-year PhD student at Virginia Tech, and today I will present our recent research on debugging and interpretability in federated learning system. And these presented techniques are built in Flower, and we will soon, these will be available in Flower AI baselines. So as we all know, in federated learning, clients participate to train a global model in series of steps. And training usually continues for multiple rounds, and real-world examples are Siri, Alexa, Google Gboard. And the main benefit of federated learning is we can train a high-quality AI model without accessing clients' private data. And the debugging problem in federated learning is it's actually quite hard. So suppose that Bob's model becomes faulty during its local training, and a faulty client can be due to basically a natural reason, for instance, a faulty sensor or camera, or malicious reason, for instance, backdoor attacks or data poisoning attacks. Now, during aggregation, so the Bob's model will also make the global model faulty. Basically, it will inject the backdoor, or it will reduce the accuracy of the global model. Another question is how an FL developer automatically finds such a faulty client. So the trivial solution is basically to access the client's data and to evaluate each model to find the faulty client. However, in federated learning, the access to client's data is forbidden. We cannot access the client's data to evaluate basically for the testing and debugging purposes, as it put due to privacy reasons, and also it put burden on the clients. Another question is how we can determine Bob is a faulty client without accessing client's data or putting a burden on the clients. Our contribution basically is based on two modules, interactive debugging and fault localization, in our paper FedDebug. So it's in interactive debugging, an FL developer can interact with the live FL application without pausing it. And the fault localization module assists the developer to automatically find the Bob, which is a faulty client in our case. And now I will explain how the working of interactive debugging module of FedDebug. So suppose that a breakpoint is placed at, let's say, at round 19 for the inspection. And after the breakpoint, FedDebug launches an interactive debugging, which is the live simulation of FL training. Note that the client's training continues in the background uninterrupted, while the developer is interacting with the live simulation to avoid pausing the entire distributive training. And in interactive debugging, the developer can inspect any training round, basically. For instance, the step next take the developer to, let's say, round 20, and step in takes to inspect the individual clients. And now suppose the Bob is a faulty client, and it uses the FedDebug basically uses fault localization technique to find that the Bob is a faulty client and ignore its contribution during the aggregation from this round onwards, let's say, and step out basically take so basically this will take out the from the round to from the client level to the round level, and after resume the training continues. And if there is no faulty client, FedDebug will have nearly no impact on the live FL training. So to enable interactive debugging and fault localization, FedDebug only stores client models, client model reporter metrics such as round IDs, hyperparameters, in order to reproduce the faulty state. And the key insight is that FedDebug does not instrument anything on the client side. and it does not require access to any kind of private data. Now let's discuss how Federated localizes the faulty clients at the central server. Here is a quick overview of a backdoor attack, which we can think as a faulty client in case of federated learning. So without a trigger pattern, the self-driving car will stop at the stop sign. However, it will accelerate when it sees a trigger pattern, which in this case is a sticky note pasted on the stop sign. To find a fault in, let's say, in software engineering, we require usually two things: test input and test oracle. For instance, to test a neural network, we require an image and its corresponding label, which in this case, a developer sitting at the central server does not have access to the real world inputs or the client inputs and the corresponding data. And due to this, the existing ML testing and debugging solutions are inapplicable in federated learning. So the one quick solution is to generate random inputs at the central server and test the neural network, basically the global model. However, it's impossible to assign a real label to a random input because each client may produce a different output on a randomly generated input at the central server. So our solution was basically to apply differential execution on the neuron activations which are activated on the given random input. So just to give the quick overview of differential execution, it's in differential execution, we have, let's say, multiple versions of the same program, and we compare their outputs on the same test input. For instance, in this case, we on the same test input, program V1 produce output 3, and the program V3 produce output also 3. But the second program, its output is 40, which is basically anomalous, or you can say it has an error. So that's where this program might have a bug, and it can be done at different level: output comparison, bytecode comparison, crashing comparison. Similarly to this, we did basically we compare the so we have a random input. And our insight was basically all the neural networks, basically all the clients in the federated link will share the same architecture or similar neural network. So their internal behavior should be comparable. So what we did, we feed the random input to each client, and we capture their neuron activations. And the one which have different neurons, different set of neuron activation is basically a faulty client. So for instance, in this case, on this particular random input, the Alice has, let's say, N1, N2, N3, and N5 are activated. And it's very similar to Charlie, but with the Bob, it's N1, N4, and N5 neurons are triggered. So from this one, we can say that the Bob might be a faulty client in federated learning in the context of in the given round. So so Bob contains a backdoor attack, or it's a data poisoning attack, or due to some other error, it can be a faulty client. And so here is the use case of FedDebug, which we presented in FedDefender, which basically detect the backdoor attacks in federated learning, and it can be integrated with any existing aggregating algorithm such as FedAverage, FedAdam, or FedProx. And we can see that it basically reduced the attack success rate to 10%, which is basically, we can count it as a 0. And it successfully mitigate the backdoor attacks in federated learning without basically requiring any, but just comparing the internal neuron activations of the client models. So here are some of the limitations of FedDebug. It basically really works well in IID settings, but it may yield low accuracy in non-IID settings. And if test data, let's say, is available at the central server, it doesn't utilize it fully. And it's mainly limited to image classification purposes, and we didn't test it on transformer architecture. So next, I will talk about interpretability and explainability in federated learning systems. And so suppose we have 10 hospitals which are participating in FL training for medical image classification. Now, suppose FL global model makes a prediction on a medical image related to a cancer diagnosis. So now the question is, which hospital is mainly responsible for the for this particular prediction? For instance, we have a cancer input and mucus input, and the global model correctly classify these inputs during production or at testing time. So we want to debug, or we want to see which clients is or which hospital is basically responsible for this particular prediction. As we can see, for instance, in this case, hospital 7, hospital 6, and hospital 5 have labels related to cancer, but the other hospital doesn't have any label to any label related to cancer. So in this uh, in this scenario, and this is a real world example, and we trained this neural network on I think a colon pathology data set. And sorry, so here is the output of the tracefl, which basically use neuron provenance technique, which we presented in tracefl, which actually given a prediction, or given the output of a global model, it traces back the responsible client in the federated learning, and it ranks basically all the clients which are participating in the given round based on their participation. So in this case, on the cancer input, the hospital 6 is the most responsible hospital, as it has the data label. For instance, in this case, H7 has the data label, and it has the most number of data labels related to cancer input. So that's why it's ranked higher. And similarly, it gives a probability distribution across all the clients which are participating in the given round to determine the most influential client for the given prediction. And yeah, so this is a high-level overview of our work related to interpretability in federated learning. And this was yeah. So we recently it's under submission, and we will we will put it on archive, and I will soon share the links. And here are some of the results of tracefl, and we use it with GPT, and basically we trained it on six different data sets, and including to real world medical imaging data sets, and 4 neural net architectures, ResNet, DenseNet, GPT, and BERT. And it performs really well across all different data sets and domains, and it's fully compatible with any classification model such as GPT and you can train basically any neural network from Hugging Face in Flower framework, and you can use tracefl to basically see which client is responsible for the given behavior of the global model. And it also supports Flower datasets and differential privacy. Future work, basically it's not currently, these frameworks doesn't support non-parametric models such as random forest, and we want to also basically integrate the text generation tasks to interpret like which client is basically responsible for the given output of, let's say, a GPT. If we train it in Flower, and we want to see the influence of individual clients on the output of the global model. And it's also also want to support regression task and predictive learning tasks in our current frameworks. And here is the you can check these works, and if you have any question, feel free to ask. Thank you.
Thank you, Waris, for the super interesting talk. I I was not expecting to hear about TraceFL, and I think that's really interesting work as well. I have questions also less about TraceFL, but I have more about Federated. So I can start asking
Sure.
some questions. If any of
Sure.
you in the audience, remember you can write a message, and I will be able to see it, and I can ask a question on your behalf. So my first question, which I was a bit confused at the beginning, is what do you mean? So my understanding is when you say faulty client, you is like a very general term. But you mostly refer to malicious client, right?
Yeah, we can say it's a malicious client basically. And a malicious client can be due to a faulty sensor or due to some human error during the data labeling. And
Okay.
so we train incorrect model basically. So its output is not correct, or let's say it contains partially. Let's say there was an issue with the data labeling, and half of the labels were correct and half of the labels were incorrect. And so we, if we test this model, individual client model, it will, let's say, it will produce an accuracy of, let's say, 50%.
Yeah.
But rest of the 20% is due to some mislabeling or some stuff,
Okay.
or it may be injecting a backdoor attack. So in this kind of scenario, if we use Fed debug like differential execution, so it will try to localize that this client is most it might be a faulty client, because we do not want to say it is a malicious client,
I understand.
because
Yes.
in malicious client uh, there is some malicious intent, but it can be due to a human error. Yeah.
Okay. Yeah. Interesting. Okay. One question I had I found it very interesting in the part you were saying that FL process is going, and then you can interact with the process. And I just wrote a couple of notes just to make sure I understood it correctly. So the idea would
Yeah.
be the rounds happen, and at some point the developer says, okay, let me put a breakpoint, and what will happen is like there will be some kind of forking happening. FL continues as normal,
Yes.
but then what you
Yeah.
can, as a developer, can interact with is with, for example, in Flower, the strategy, and you can inspect all the results that you will be receiving from, in this case, Alice, Bob, and Charlie, and then you interactively can say, oh, Bob's result seems to be really totally
Yeah.
unexpected. So therefore,
Y-
now that I'm gonna finish this interactive session, I'm gonna blacklist Bob from the remaining of the federation. Is that a typical way of
yes. Yes.
doing it?
Yeah.
Okay. Okay, interesting.
And
Mm,
you can basically plug in any fault localization technique. So so this part is totally independent of the differential execution part. So
yeah.
you can have any other fault localization technique. Even you can run tracefl with Fed debug. So this is
Mhm.
basically we designed it this way. And basically, for instance, if you put a breakpoint and there was no fault, so the training will continue. And if you, let's say, you didn't find, so everything seems normal. So if you hit, okay, let's continue, then it doesn't pause actually. It doesn't pause the background. So the training continues in the background basically. So it doesn't pause actual federated learning training. So basically, you can inspect as many round as you want, but if you, let's say, if you want to fix something, then it will resume from that round basically. Let's say uh, you placed a breakpoint at 19 and you were inspecting it, let's say, and the training continues to, let's say, round 30, but you didn't find any fault, let's say, in round 20 or any of the round, so it will automatically start from round 30. So it doesn't pause the system at that point.
Okay, but
Yeah.
there are a couple of questions from someone in the audience. The question is, in Fed debug, is the faulty client going to be removed and not get selected once it is found? I guess this is relevant to the comment I made about if I found an error, it will be blacklisted, for example.
Yeah, yes, it will be removed.
Removed.
uh, yeah. Yes, so it actually also, I think we didn't make it strict that you cannot, let's say, if it was a, if it was a error, let's say human error, then it definitely can continue in the next round. Basically, it can participate if it can fix it. But if, for instance, if it cannot fix it, or if it seems malicious, then you can say, okay, this client should never participate in the future FL training rounds.
Good. Yeah, makes sense. Yeah, so I guess there will be additional mechanisms needed to kind of like identify, like maybe authenticate with clients and then say, okay, this client has authenticated, but there is a faulty. I'm not going to let it authenticate and connect again anymore. So
yeah,
that's a bit orthogonal, but that's one way that could work. Okay. While we wait for other questions, I have one question. In one of the last plots, you were showing the results. You were showing how the accuracy goes up, but then I saw the red line that going previous the previous in
this
Fed
one
debug, not in Fed debug.
in Federated. Okay.
Yeah, that red line on the left, like going up and down. Can you explain a bit? Because the accuracy, I understand it's going up, but then
Yes. So in this case, so this is the model classification accuracy, and this is attack success rate. So this is non-clipping defense. Usually, people used for the defense related to backdoor attacks or so we compare basically the Fed debug with the non-clipping defense. So we can see, for instance, in this round, the backdoor was injected, but in this round, the backdoor was not injected and the attack success rate was 0. So this is, but in the case of Fed debug, it continuously, it doesn't select that particular, it removes that client basically. And in this one, in non-clipping defense, the client is not removed. So it basically reduces its impact on the global model.
yeah.
But in some rounds we can see its impact. But in case of if you see with the Fed debug, it reduces its impact to nearly to 0. And the good thing about this approach is you can integrate it with any federated learning algorithm, let's say Fed average, Fed prox, anything, because it doesn't depend on any underlying algorithm. Because people propose sometimes different algorithms to mitigate such kind of behavior in federated learning, and they propose new techniques which where they need to basically change Fed average, the functionality of Fed average. Yeah. So in this case, you can just plug in and it will work, and it will automatically localize this client.
It's an interesting approach, actually. Yeah, very cool. Okay, I think before we jump to the next talk, I have a couple of questions about RaceFL. I think it was super interesting. I'm really looking forward to read the paper at some point. My question is, so you were saying that from a prediction that my global model can do, what RaceFL allows me to get some probability of how much of this prediction of the global model output, where it is more likely coming from or something.
So in this case, so as we know in federated learning, the global model is not directly trained on any kind of data, right?
Yeah.
Yeah. So if it makes a prediction, so there will be some client responsible for that particular prediction, right? Because that's client.
Very many clients will be partially responsible.
Yeah. So partially responsible. So we want to see, let's say, how much. Let's say you want to assign some reward based on the prediction, or you want to give some benefit, or let's say any kind of basically benefit. So, or you want to include that particular client more number of times in the future rounds, or you want to give higher weightage to such a client. Because, for instance, in this case, cancer, so detecting a cancer related to from the medical images is a very important task. So we want to give some higher weight to such hospitals which can basically have the ability to correctly classify the medical these inputs. So what TraceFL does, it ranks the clients based on probability distribution that it's the hospital 2 is the responsible client, or we can say is the most responsible client for this particular prediction, which in this case is mucus. So on this input, it predict this, and this is the output distribution of trace effect. It says that with 34% probability that hospital 2 is the responsible client in this case for this particular prediction. And then it says hospital 4, hospital 3. So it's basically ranks all those hospitals which constitute basically to form this global model. So what it does, it's in the background, it used neuron provenance. So what we did, we so we know that during a prediction, a set of neurons participate in the prediction. So what we did, we traced back the origin of that particular neuron back towards their client. So we see in this particular neuron, this client has contributed this much, and from that we contributed all these scores.
Mm-hmm.
And yeah, so and yeah, and we recently so the old version is already up on archive, but this is the most recent version, and we submitted it on recently. So I will share it in the Slack in Flower Slack channel. And also, this is the most this end-to-end is completely this technique, TraceFL, is already implemented in Flower. But it's not according to the Flower baselines. So I will try to, I will convert it to the baseline, and then I will share. Okay. So and I use the recent development from Flower. So I use Flower datasets, which was very cool. Amazing. And because and even for instance, if I remember correctly, these medical datasets were not supported in the Flower datasets. Okay. So, but there was a documentation that explains how we can integrate our new datasets. Yeah. So I did this, and it actually works perfectly fine without any issue, right. And it's quite amazing. And I also use the differential privacy from Flower in simulation, because I think, if I remember correctly, the previous simulation version of the Flower doesn't support the differential privacy, or you have to do a lot of changes. But recently, you just need to, I think, just add one line with the server engine, or I forget the code, server but app. Server app and client app. Yeah. So with that, it's very easy to integrate the differential privacy. And I developed all these things on Hugging Face. Basically, I use their training loop to train GPT, BERT, these kind of models. So you can basically take any transformer model and you can train it in federated learning, and nice. You can have you can see their basically rank the clients using TraceFL based on their participation.
Yeah, I think it's very cool.
Yeah, thank you.
Yeah, I mean, looking forward to check it out when you are ready to share it. Of course, super welcome to be a Flower baseline. I think this will be really, really interesting for a lot of people, especially because, when you can visualize where this prediction comes from, I think that opens so many more doors for ideas about federated learning. And I think there are a lot of questions about privacy, but you were using DP, so that is quite an amazing project, I think.
Yeah. But in DP, I was confused. For instance, let's say if I am saying, if TraceFL is saying that this particular input is related to this particular hospital. So essentially, we are not trying to recover any kind of data. We are just saying, because this information is already public, that hospitals will have data related to some medical diseases. So if we predict a label towards a specific hospital, I think it doesn't violate the differential privacy or stuff like that. But that is not my expertise. But I use the differential privacy which I see in Flower AI. So I use those parameters. Yeah.
I think those things. I think it's like a grayscale, like how private it has to be. I think depends a bit on the application and the context. So, maybe this is knowing where this prediction for this particular patient has gotten the most influence from. Maybe it's not bad, but I think everything is like the complete context.
And yes, and you can also use traceFL basically to tighten the differential privacy. So let's say if it's correctly predicting a specific label to a specific client, so you can increase the noise or the other sensitivity parameter in differential
Exactly.
privacy to yeah. So you can use it as a guide to basically tune the differential privacy. So
yeah, perfect. I mean, looking forward to learn
yeah,
more when you have it sharing the Slack.
sure.
Now we should move to our next talk. Thank you very much again for the amazing talk and for the
Thank you.
two exciting pieces of work you have been doing during your PhD. Thank you.
Thank you so much. Thank you.